All right, good job. That's pretty much it. All right. So that's one purpose of, or one way to use the YouTube videos is kind of before class you can reconnect to what the previous class talked about. And you might find it helpful, especially over the weekend, because it's a little bit harder to remember, what we talked about 5 days ago. Is that okay? So I highly encourage every person in this class to kind of do that, to remind yourself, what we talked about like 5 days ago. And so let's go ahead and get started. So I did close down Logisim, so I'm gonna restart, but it's pretty easy to get back to where we were. So what I'll do is I'm just going to go through the process to get back to where we started, and then we'll continue from that point. The program that we wrote last time only had 2 instructions, and I still remember the opcode. The first one is 8D, and the second one is 01. 8D is the subtraction instruction, and then 01 is the halt instruction. So I'm not gonna, repeat, what we did last week to get to this point, and instead we'll go from here and quickly go through the process of clicking Control T, which each Control T is one edge of the clock. So if the clock is currently low, Control T would go up, and then another Control T would go back down again. So this is where we start, location 000. The rising edge of location 000, or when the ROM is at location 000, is also known as the fetch cycle. So if you have not written down, this is called the fetch cycle, you might want to write it down on your own in your own notes. Okay. So the fetch cycle only has one thing to do. It goes to where the program counter points to, retrieve the content at that location in RAM, and put it into the instruction register. That is what the fetch cycle does. So once I do a Control T, you would see that the opcode, which is 8D at this point, is inside the register instruction register. And the falling edge doesn't really have a name. All it does in this case, the falling edge, is to continue on to the second instruction or the next instruction in ROM. So when I have Control T again, you can see how the ROM, the microcode pointer, increments from 000 to 001, and we get to the second location. So when we get to the second location, the rising edge really has no particular name other than auto-incrementing the program counter. So when the reason why we are auto-incrementing the counter, the program counter, is so that the pointer to RAM is now pointing to the next available instruction. Because the one that we were pointing at is already stored in the instruction register. There's no need to point to that location any further. Is that okay? So this particular rising edge Control T has no particular name other than incrementing the program counter, and we can check and make sure that the program counter is in fact incremented from 00 to 01. The falling edge of this particular cycle does have a name. So the falling edge of this particular cycle, when the microcode pointer is at location 001, is called decode. D-E-C-O-D-E. So it's for decoding the opcode so that we can figure out what to do with that particular opcode. So once again, if you have a piece of paper or if you have some way to record it, you might want to write down that this is called the decode cycle. It's only for this particular edge. Yep. So this edge is called decode because we are looking at the opcode that is currently stored in the instruction register, and then we go to the right place in the ROM so that we know exactly how to configure all the components of the processor in order to carry out the instruction that is represented by 8D, which is subtraction.
So it's called the decode anytime those instructions.
Correct. Yep. So this is the decode cycle in terms of the execution of instructions. So this is also the magical moment because the moment I hit Control T, you will see that we're no longer going to we're no longer at 001, but at the same time, we're not continuing with 002 either. We'll go straight to 8D0. The reason why we go into 8D0 has to do with the instruction register has 8D, and then this particular merger is changing. It's basically left shifting the instruction register content by 4 bits before it is used to update the microcode pointer. Okay, so the next edge, okay, the next time I press Control T, the microcode pointer will change to 8D0, where the configuration bits are specific for this particular instruction. So Control T again. So this is decode, and you can see how we went from 001 to 8D0. All right. So because this part we have already explained on last Wednesday, and I just kind of went through a really fast recap of what we talked about on last Wednesday, you really should understand how we got here. Okay? So if you are doing this by yourself and you're going through this whole process and you're saying, well, but I'm not really fully understanding how we got here, you either spend a little bit more time with the processor architecture or ask questions. Okay? But you are expected to understand how we got here. Okay, once we get here, what are we doing? Well, the first thing is there's a whole bunch of bits specified by this location in ROM. 150D7F8, if you want to translate these back into binary digits, it's pretty easy, right? Because every hexadecimal digit is 4 bits. So if you want to spell this out, it is 0001, 0101, 0000, 1101, 0111, 1111, 1000. There's no need to write it down, okay? Because that's just me translating the hexadecimal digits back into the 4-bit patterns, okay? But the question is, what does that mean? Well, all of these bits, individual zeros and ones, are going out of the D port. So once again, the D port goes to a whole bunch of tunnels because I don't want to draw a bazillion wires that are crossing over each other in the design. So it goes into microcode data, RAM load, RAM select, blah, blah, blah. Okay? So remember what we did on last Wednesday? We want to look at components that are active. Okay? And then from the components that are active, we try to figure out what it is trying to do. Is that okay? So the other thing that I forgot to do, not you, but I forgot to do, is to give ourselves 2 actual values to compute. So we need to go to the register bank. It's not too late. It's almost too late, but not yet, to actually give ourselves a few things to calculate. So I'm going to go into the register bank, and if I remember correctly, okay, it's a D, so it's 1101. So we are subtracting register B from register D. So we are subtracting register B, and let's call this 1E, and let's call this 07, okay? I'm pretty sure this is not the example that we used last time, but I'm just going to use this one for now. What do you think is the result? We are subtracting 1E from 07. What do you think which register should be updated? And it's kind of visual, unfortunately. And when it does update, what should be the new value of that particular register? So let's answer the first question first. Which register are we supposed to update? Register D. We can visually tell because only the enable of register D is a light green. So that's going to be the one that's going to be highlighted. What value do you think it's going to be when we update it? In other words, I'm asking you, what is 07 minus 1E as hexadecimal numbers? Okay. Well, first of all, do you think we can do this by hand? Okay. And if we're going to do this by hand, let's figure out how to do it. So I'm going to go into mousepad. Okay. And do the usual thing that I do. 07 minus 1E, but these are all base 16 numbers, right? Okay, so we can do it exactly the same way as we always do, which is maintaining one row for the partial difference and one row for the borrow. All right, what is 7 minus E? Not counting the borrow or anything like that. Sorry? So how did you learn that 2 minus 5 in base 10 is 7? It's the same thing. It's the same exercise. And of course, nobody can remember how you learned something in elementary school. Yes? No? Isn't that elementary? I know you guys are not Watson,
I
but
did it with jump rope.
jump rope? Go ahead.
Say that 2 minus 5 is 7?
2 minus 5 is 7 in base 10
Oh, no. 2
with a
minus
borrow. That's the result. That's the R, right? Okay, so how did you guys learn that that is the case? There are two ways to do it. One way is to use a number wheel. So we use a number wheel for base 10 first. So we got 0, 1, 2, 3, 4. Okay, it's not exactly even. 5, 6, 7, 8, 9. Okay, it's an ugly number wheel, but it still works. Okay, so here's 2, and I ask what is 2 minus 7, right? 2 minus 5. Okay. See, I cannot remember what I just said. So we go back 5 steps. 1, 2, 3, 4, 5. There's 7. Now, how do we know there's a borrow? It crossed over from 0 to 9. So those are the easy things they can do kind of in a visual way. Is that okay? Does that make sense to you that this is how one way to learn about subtraction? Okay. So now we change this wheel to make it a base 16 wheel, which is a whole lot easier to draw. Okay, because base 16 is a power of 2, which means I just have to find midpoints until I have the correct number of notches. So this one looks a lot better. Yes? Okay, so we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, because it's in hexadecimal, so that means we have to borrow 6 letters from the alphabet to represent from 10 to 15. Same question. Okay, we got 7, and we want to subtract E from it. E is 14, so there's a long way to do. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. So that means we have to, I almost used this on the projection screen, which is not a very good idea. There we go. Is that okay? But we also have a borrow. How do I know that there is a borrow? We cross over from 0 to F. Okay? So there's a borrow. Where does it go? The usual place, right? All right, so now we have 9 minus 0, which is not too bad, because anything minus 0 is that something back. We have 0 minus 1. Okay, so once again, what is 0 minus 1? We start here, minus 1 is F. But we also have a borrow, because we just cross over that 0 to F border. So this is F with an overall borrow here. F minus 1 is E. Oops. There we go. So we're expecting E9 to be stored in register D when the instruction is done. Are we doing okay so far? Okay. As a nonlinear learner myself, okay, I'm just eager and go like, is that really the case? Check it first, okay? And it is not. So was it an addition? Oh, this is an addition, not a subtraction. 9D specifies a subtraction, not 8D. 8D is an addition. It's okay, we can go with the addition. So, but does it make sense that it is 2,5 in hexadecimal when we add 1E to 0,7? E is 14. 14 plus 7 is 21. 21 minus 16 is in fact 5. But because 21 is greater than 16, it also has a carry. So that carry gets added to the 1 here. So we got a 2. So 2, 5 is the correct result. Okay. Did we use an addition or subtraction instruction on last Wednesday? It was addition? Okay. Okay. Well, slightly different numbers. I could hard code this to change it to a subtraction now, but I don't want to add any confusion to the process. So we'll just go ahead and go with the addition, okay? So everything is set up correctly, but now the question is how, right? I mean, the input into the register bank, this Y here, is already correct. How do we get the correct result of register B adding to register E? So that is the big question, okay? This is also the technique that I want you guys to practice when we talk about different instructions. So whenever I give you a new instruction, you need to go through this exercise to find out how the instruction operates, okay? Now, there are 16 variations of add. You don't have to do the same thing with all 16 variations of add because they're all just specifying different registers. But there are 20 to 23 individual instructions. You might want to try this with every single instruction. There are only 20 something. So now we want to ask the question, who is doing the calculation? Who is enabled other than register input at the register bank? So if you just look at the green, light green wires, who is active? Who, as a kind of more important component, is active? The ALU, okay? The ALU is enabled. Now you might say that this particular demultiplexer is also enabled, okay? Well, you're absolutely right. It is enabled. But multiplexers and demultiplexers are like railroad switches. Can the railroad switches actually do any processing or move anything around? By themselves, the answer is no. They cannot do a single thing. All they're doing is to say, this input now is going through that output, or this input is now going through that output, okay? So by themselves, they're not really useful. So that's why we don't start with tracking the multiplexers or the demultiplexers. We track down the factories, okay? We track down, which station has people in it, okay? We track down all those things. So now we have a factory, okay? You can look at the ALU as a factory because it has got input for quote-unquote raw material, and it also has an output for the finished product. Are we doing okay so far with this analogy? Yes? If this is not visual and too abstract, we can go for a very short off-topic video of Thomas Train factory. And we'll just look for an image as much as I want to watch a video. Oh, toy factory is not a good idea because it just shows toys. Okay, fine. Get rid of toy. No, it has got factory. Okay, how about this? We add map to it. I think one of my, this just went bad. That's okay. Oh, this is a good one. I like this. I like this a lot. All right. And you might think, but this is way off topic. I would disagree. This is not off topic at all. Oh. Can we open it? Nope, because I don't have a Pinterest account. I actually do not. Oh, I see. Gotcha. Right click. We'll see. There we go. Okay, excellent. Let me fix the battery of this thing first while you guys study this. It will be in the test.
Just let the people watching the stream think we're having an in-depth discussion.
We are having a very good intellectual discussion right now. You can learn a lot about social interaction using Thomas the Train. What's the name of the show? Thomas the Tank Engine. That's it. Yep. Okay. So, what does this picture have anything to do with processors? Well, do we see similar, or equivalent or analogous components between this picture and the processor schematic?
Bunch of multiplexers.
It has got a whole bunch of multiplexers. Exactly. So point out, where do we see the multiplexers?
Bottom left.
So we got one here. Okay, we got one multiplexer over there. We got one over here. We got one over here. And then we have, something that resembles like a processor, like right here. The register bank, I think we are missing that because we don't have the station where all the trains, reside in this picture. So why do I point at this thing and say it is a multiplexer or demultiplexer, since we don't know which direction? Why? It's a switch. Okay, it is a switch. Now, if you go through, all the toys that you can buy for Thomas the Tank Engine, you will see that there are actually tracks that are switchable. This one is not, but there are actually tracks that are switchable. So switching back to what we are talking about here, every time you see something like this or this or this, it's basically equivalent to the Y pieces, except these are a little bit more complex. There are more tracks, and it also has a control mechanism. But that's basically what they are. They are not useful by themselves. Okay, they're only here to help route things around. So we know that the ALU has to be active because it is an addition operation. Only the ALU can perform operations. Okay, so when you're talking about adding, subtracting, comparing, bit shifting, and whatnot, only the ALU can perform those operations. So when you specify an add operation, it is not surprising that we have to route things into the ALU. The provider of the content is over here. It's the register bank, because we are adding register B to register D. So looking into the register bank, we want to make sure the register B is going out to one of the ports, and we want to look at register D and make sure it's also going to one of the ports. How does it get done? Okay, so when you track down the output of register D and you track down the output of register B, how are they getting routed to the output of the register bank? The multiplexers. Very good. So the multiplexers is what's doing it. But how does the multiplexer know which input to route to the output? The selects. Okay, we got 1, 1 here to select register D, and we have 0, 1 here to select register B. Is that okay so far? Okay. So that is why the output pin for register output 0 is the content of register D. It is also why register output 1 has the content of register B. Is that okay? All right. So now we know, how the register bank is outputting the contents of register D and register B. Then how does it get routed to the ALU? So register output 0 goes through this particular demultiplexer, and it has to choose this route, right? It has to choose output 1, but when you look at the select, it is 1. So we got the right one. When you look at register output 1 from the register bank, it has to go through one demultiplexer and one multiplexer to get to input 2 of the ALU. So it has to first go through the output 1 of this demultiplexer, and this select line confirms that we are in fact we're connecting the input to output 1. When you look at this particular multiplexer, this one is harder to see, but this is actually connected to the select line. It is a dark green, which means we're selecting input 0, which is what is highlighted right now, to the output of this particular multiplexer. And this is how we got register D to here, and this is also how we got register B all the way over here. Are we doing okay so far with this analysis? We start with the things that actually do something useful or that can store information, and then we trace the rest of the tracks or the switches to make sure that it is routed correctly. So we also want to know what operation is being specified. So the SEL for the ALU, otherwise known as OPSEL or operation select, is what specifies, what operation we are trying to do. 0, 0, 0, meaning that there are 8 possible operations inside the ALU. 0, 0, 0 chooses the first one, which turns out to be the adder. Okay, so this is how we know that we are selecting let's add, and what are we adding? The first input connects to register D, the second input connects to register B. So if you look into the ALU, you will also see the same thing. Input 1, we got input 2, but when you look at the select of these two demultiplexers, they're both selecting 0, 0, 0, and the other one is 0, 0, 0 as well. So that means this input is routed to this particular output pin, going to the first input of the adder. This input, on the other hand, is routed to the second pin, the second input of this particular adder. So this is how we can add those two numbers to get the result. Okay, so this is where we got the 2, 5. Okay, because the adder is what is doing the calculation. But this 2, 5 has to go through this multiplexer to get back out of the ALU. So let's figure out how this is being selected. This is input 0, but when you look at this particular select line, it is also specifying 0, 0, 0, which means we are routing input 0 to the output, and this output goes to the output pin of the ALU, and that's how it appears on the overall diagram. That's how the output is now having that particular result. Is that okay? That result is going through back to this multiplexer. This multiplexer is switched by RIMUX, but since it's a 1, it is selecting input 1, which is the one being highlighted right now, to the output. And that is why the register bank is now receiving 0010, 0101 as the content to update one of these registers. But we already saw that register D is the one that is going to be updated, right? Okay? So this is how the add instruction works, okay? This is also how we specify the microcode of a processor, is we just specify exactly how the switches should be configured. We also specify which components should become active. And so when we have a rising edge, then register D will update to hexadecimal 25, which is the correct result to store back into the register bank. So we're doing okay so far with this particular example. Is that okay? All right, cool. There's nothing else that is active. So if you look carefully, well, the flags register is active as well, because we want to store the flags corresponding to this particular addition, and we'll take a look at that in just a moment. RAM is not selected, so you can forget about this whole thing. It's not doing a single thing. Let's see, the instruction register is also not active. Okay, you can see it is not going to be updated, so that's good. The program counter is also not going to be updated. So in this particular on this particular rising edge, the only thing updated is going to be the flags register, which stores the result of the flags after a computation, and also register D inside the register bank. Those are the only two things to be updated. Are we good so far? Are there any questions? Nope? Okay. So now the question is, what is the content to update the flags register? Okay, so we have to kind of think about what flags we can expect. So let's go to the register bank, because now we can actually see the two numbers being added. Okay, what about the carry flag? The carry flag is bit 0. Do we have a carry when we add 1E to 07? Okay, if the borrow flag is to cross over this, the carry flag is to cross from here to here. Okay, so the question is, do we have a overall carry? No, we do not. The overall carry is talking only about the most significant digit. The most significant digit is going from 1 to 2, right? Going from 1 to 2 does not cross over F to 0. So there's no overall carry. The overall carry is a 0. Is the result a 0 itself? Well, quite obviously it is not, right? It's 2, 5. 2, 5 is not 0. So the Z flag is also going to be a 0. How about the sign flag of the result? Do you think the result of the computation is has a sign bit being a 1? What is the sign bit? Correct, but position-wise, where is the sign bit? It's bit 7 of the result, right? So if you look at 2, 5, is bit 7 a 1 or a 0? It is a 0, okay? So the sign flag is a 0 as well. Do we have overflow? When you add 0, 7 to 1e, are the signs making sense? If you look at 1, 0, 7, it is non-negative. When you look at 1e, it is also non-negative. When you look at 2, 5, it is also non-negative because the sign bit of all of these three numbers are zeros. Does it make sense when you add a non-negative number to a non-negative number, the result is non-negative? Yes, so there's no overflow. The L flag is the exclusive OR between the sign, which is a 0, and also the overflow flag, which is also a 0. What is 0 exclusive OR with 0? 0. So now we have just briefly mentioned and also calculated the 5 flags that we need to use. The C carry flag is a 0. Z flag is a 0. The sign flag is a 0. Overflow is a 0. And the L flag is also a 0. So that means whatever is going into the flags register, those 5 bits, they should all be zeros. So we will double check and make sure that is the case because the flags register is about to be updated. So this confirms that this particular addition will turn every single flag 0. Is that okay? So I think we're ready for a control T or rising edge. So upon the rising edge, you will see that the flags register appears that it has not changed, but it actually is updated from 0, 0, 0, 0, 0 to 0, 0, 0, 0, 0. But when we look into the register bank, you will see that register D is now storing the result of the addition, which is 2, 5 in hexadecimal. So the instruction has basically accomplished what it is supposed to do at this point. Are we agreeing that the instruction is done with what it is supposed to do? So at the end of the execution of one instruction, what do you think the processor should do when I click the falling edge? Sorry? Well, we're done with one instruction, so we have to start with the next instruction, right? So what is the starting point of the execution of an instruction? I asked you to write this down a little bit earlier. It's location 0, 0. Go ahead. It's the fetch cycle. So we want to go back to the fetch cycle. So in order to get back to the fetch cycle, you go look at the ROM. Okay, so we go back to the main diagram, and then we look at the ROM, and we ask, what is right after location 8D0? So right here, and I don't think I can scroll. Yeah, I cannot scroll here. So the only way to look at the location or the content of location 8D1 is to right-click, edit content, go to 8D something. I just passed it. So we have 8D0 here. This is 8D1. 8D1 is 2 followed by all zeros. It has the most significant bit of the output being a 1, and everybody else is a 0. So we want to track that down. It's like, why is that special? So I'm going to close this window, and then we track down the most significant bit of the output of the ROM. This is the data port. This wire is representing the most significant bit of the content of the ROM. Is that okay? Because you can see from the splitter, it splits from bit 0 to bit 25. Bit 25 is the most significant bit of this ROM. It will become a 1. Okay? It is a 0 right now because we're still on location 8D0. But when I do a falling edge, it will become 8D1. Okay, and at location AD1, this particular bit, the one wire that is highlighted, will become a 1 when everybody else will remain as zeros. Okay, so now the question is, what is it going to do? So we want to look at how this wire is connected to the rest of the circuit. This wire connects by a OR gate, okay? So as an OR gate, if at least one input is a 1, the output becomes a 1. So that means upon the falling edge, this output will now become a 1. Where does that connect to? It connects to the microcode pointer, but exactly which port of the microcode pointer, and what is it going to do to the microcode pointer? This is not enable. It's a 0, which means it's going to reset. Okay, it's going to 0 or reset the microcode pointer. And by doing that, it is going to 0 the content of the register, which means we're going to go back to which location? 0, 0, 0. Because we will be ready to begin which cycle? The next fetch cycle. Exactly. So we'll do exactly that, okay? Because we'll do we'll do a falling edge right now, and you can see how it blinked, and then it just went back to location 0. Okay? So this is fetch again. Which location are we fetching from this time? Okay, so first of all, which register should we look at if I need to know which location I'm going to go to fetch the next opcode? I know it is ambiguous. I did not say RAM or ROM, okay? I did not say which register, but I say that specifically, but I did say one word that it should give you the clue to tell you which register we should be looking at. I did say opcode, okay? I said, which location should I go next to get an opcode? So now in your head, you should be thinking, there's RAM and there's ROM. What does RAM store? What does ROM store? Which one stores opcode? No. Very good. It is RAM. Okay, so RAM stores opcode. ROM stores microcode. Okay, ROM stores microcode. So if RAM is storing opcode and I'm about to grab the next opcode, which register will tell me where I should get the next opcode? Which register connects to the address port of RAM? We looked at it earlier when we fetched the opcode for 8D. We also did it last Wednesday. So which register connects to the address port in order to get an opcode? This is a very important register. It's called a program counter, otherwise known as PC. Okay? So the program counter is going to point us to the next location. This is what you kind of need to do, is to kind of go through this whole exercise, but on your own, and jot down notes on the side as you go through that process. Okay? I mean, obviously, I can write all this down, or I can just go through the YouTube transcription and copy and paste it, right? But nothing beats having to go through this yourselves and write your own notes, because that will make sure that you understand something instead of, oh, I'm just going to memorize what text said. This is the program counter. It is 0, 1. It goes to this particular multiplexer. This multiplexer has a select of 1, which means it is connecting input 1 to its output. Its output goes to the address port of RAM, and you can see how RAM is now having 0, 1, the location selected. It also turns out to have the content of 0, 1, but that's coincidental. Next question, where's this D going to? This is something that we talked about on last Wednesday already. This is the fetch cycle, right? Okay, so we are addressing location 0, 1 in RAM. We are doing a read cycle, okay, for RAM. The question is, which register is going to be updated from this read? The instruction register, very good. Okay, so the instruction register is going to be updated. Okay, So the instruction register is located here. So you can see that it is going to be updated to 01 because the wire is already having the content that is coming out of RAM. The content of location 01 is 01 itself. Okay, so the instruction register is about to be updated when I have a rising edge. Okay, so I do a Control T. This is a rising edge. So the instruction register is now updated to 01. On the falling edge, only the microcode pointer is going to update. In this case, the microcode pointer is going to select input 1, and it is just going to increment. Okay, so Control T, you can see how the microcode pointer is just incrementing. Okay, so what do we do next? What is going to happen next? The next rising edge is going to, this is something that we just did today. It has no name to it, okay? We are on location 001 of the ROM. What is going to happen upon this rising edge? The rising edge does not change the microcode pointer itself, but it would change one of the other registers. We just grabbed the content of location 01 in RAM into the instruction register. Do we still need the program counter to point to location 01 in RAM? Nope, because we just read it, right? We got that content into another register now. So what should we do to the program counter, which is always going to be ready to grab the next opcode? We have to increment it, okay? We have to increase it from location 01 to location 02. So this particular rising edge will affect only the program counter. It will increment the program counter, okay? It has no particular name to it because you can see it as the side effect, of the fetch cycle. Okay, so Control T, when you go, if you scroll up, you will see the instruction register, the program counter is now 02. Now we have a falling edge, okay? So falling edge is important because the microcode pointer will get updated every time we have a falling edge. The question is, how is the microcode pointer going to be updated this time? And I think we got enough information to know how it's going to be updated. So what do you guys think? It's a falling edge. We know the microcode pointer is going to be updated. From this diagram, we can visually see that the select of this multiplexer is selecting input 0 to connect to the microcode pointer. So the update has to do with input 1 of the multiplexer, which connects to the instruction tunnel, which is basically just the output of the instruction register, which currently has 01 in hexadecimal in it. We are also going to combine this particular 0 as the least significant 4 bits into the 12 bits that we use to update the microcode pointer. So can someone tell me what is going to be the new content of the microcode pointer in hexadecimal? Yes? 010, very good. Okay, so the microcode pointer is going to update to 010, which means we're going to change which location it is addressing immediately to 010. Okay? So Control T, we have a falling edge, and it just got updated. And now we look at the ROM, and the ROM says, sure, we'll go to location 010. But 010 looks like it is not initialized. It looks like that I forgot to do something, with location 010. Can someone tell me what is the mnemonic of the opcode 01 in hexadecimal? We talked about this last Wednesday too. It's called I think it's the only instruction that starts with H. Halt. Okay, so it's a halt instruction. What does the halt instruction do? Infinite loop, very good. Okay, I'm so glad that you guys did not say it doesn't do anything. Because there's one instruction that doesn't do anything, it's called no op. Okay, so there's a huge difference between no op and halt. Halt is an infinite loop. Once you get to the halt instruction, it doesn't proceed any further. Okay? So if all the outputs are zeros, would you buy it if I just say that none of the components of the processor is active? Yeah, because with this particular design, all the enables, all the selects, they all need to be ones in order for something to be active, right? And so we are saying nothing is going to be active, okay? But even if nothing is active, is it guaranteed that we cannot move past this point? That is the next question, okay? In other words, now our concern is not so much about what this microcode is going to do, because we know all the components of the processor are basically inactive. Then nothing is going to do anything, or everything is going to do nothing. Okay, it means the same thing. But our concern is the microcode pointer, because when I have a falling edge, so the rising edge is not it's not a problem, because a rising edge affects all of the other registers, and also the ALU, and also some of the multiplexers and some of the demultiplexers. But we know all of those are off, okay, right? So we are not concerned about the register bank, we're not concerned about the ALU, we're not concerned about the flags register, blah, 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 because they're all off. So the rising edge is not a concern. Control T, okay? Now we have a falling edge. The falling edge is a concern, because where are we going to go in the ROM upon this falling edge? What do you think? It's going to change the microcode pointer, because the microcode pointer is always enabled. So upon every single falling edge, it's going to update. So the way we can tell how it's going to update is to look at the select line going into the multiplexer. It is still dark green. Why is it dark green? Because the ROM says so, right? That wire, this wire, comes straight from the ROM. So that particular bit of the ROM is a 0. That's why this multiplexer is selecting input 0 to update the microcode pointer. What is input 0 connected to? The splitter, and it connects to the least significant 4 bits are going to be zeros. What is the instruction, the tonal? Where does instruction as a tonal connect to? This is like the third time we look at this today. It connects to the output of the instruction register, which stores the opcode that we're executing right now. Now, first of all, did we get a chance to load anything new into the instruction register? No. So it still has what is the current content in the instruction register in hexadecimal? 0, 1. Oh, okay. So we got 0, 1 in the instruction tunnel. This is an additional 0. So we're going to use 0, 1, 0 to update the microcode pointer. And you guys go like, that doesn't seem to make sense, because the microcode pointer is 0, 1, 0 right now. So updating it to 0, 1, 0 means we are not moving anywhere in the ROM. But that is how we get stuck in the loop. That's how the halt instruction gets its quote-unquote job done. Is that okay? Cool? Yep.
What situation would you use the halt instruction?
So instead of using a return 0 in main, you use a halt instruction. Because in a normal C program, it does have some place to return to. Okay, main is a function, right, in C and C++. Okay, I hope you guys recognize that main is a function. So as a function, it doesn't start from nowhere. Somebody has to call the function. So what calls main? Exactly, the startup code. Okay, very good. So it is a part of the startup code that you don't ever get to see. Okay, but the linker, that works with the compiler is going to grab the startup code from the library. Okay, some of you probably know what is libc, the C library. So libc has a startup code. The startup code calls main. Okay, in other words, it has a reference to main wherever main is defined. So your main is actually being called from some code that you do not get exposed to in all the classes that you have been taking. So when main does its thing, okay, and it returns back to the C library code that you don't get to see. That will proceed to clean up your program, okay? If you have any heap, it will clean up the heap. If you have anything, it will just clean up everything. When that is done, it will do what we call a system service call. it will basically ask the operating system and say, hey, as a process, I'm all done here. Operating system, please clean up. Okay? And that's how a program stops execution normally. Okay? Is it will actually actively ask the operating system to say, I'm done, let's clean up. Okay? But when you're running a C program in Linux, when you're running a program in Windows and whatnot, what happens when that program terminates? Does your computer shut down? No. It's just going to go back to wherever it was doing before. Okay, all the other applications are still up and running, right? Your command line interface is still up and running. So that's why it is okay to do a return in main, because it just says this process is done, but the operating system keeps going. All the other applications also keep going. When you're talking about this processor, it is not. It has no operating system. The programs that you write is running directly on the hardware with no operating system behind it or underneath. So there's no such thing as return. When you're done and you say that there's no other thing to do at this point, you just get stuck in the loop. That's the only thing you can do. So is that answering the question of when we need to use the halt instruction? So every time you're done with your program in this processor, you get to the halt instruction.
So
yes?
halt is kind of like a standby?
It's not exactly a standby, not in this architecture. So in this particular architecture, the clock will still keep flipping and flopping, but none of the other components will do anything. So from the power consumption perspective, if Logisim actually does calculate power consumption, this will be a fairly low power consumption state because you only have the clock going up and down, but none of the components is actually doing anything. So there's not a whole lot of exercising of the transistors. So you go ahead and then back to you. Okay, go ahead.
All right, so for, since it's in a loop, is it just waiting for another set of instructions for us to implement?
Nope, it's not waiting for anything because the instruction, even if you change the RAM content at this point, it's still stuck because it is reading from the instruction register right now. It's not even reading from RAM. It is detached from RAM completely at this point. So there's no way you can get it out of this quote-unquote loop.
You have to reset everything.
You have to reset the processor. Yep. Go ahead.
Is that kind of analogous to when you have like a really old computer that wouldn't power itself off and it would say it's now safe to turn off the power?
Right.
Kind of what this is.
Kind of, yes.
Okay.
You're basically, because remember, the word halt, these terminology were borrowed all the way from Alan Turing. Okay? So if you think about Alan Turing, okay, first of all, the movie pops up in your head, right? Because we all remember only popular, media stuff. So the movie pops up in your head, and then I will have to ask you, right? I'm going to guide you through the thinking process. So you remember Alan Turing, you remember the movie, okay? So what was his job in the movie? An Imitation Game is the name of the movie. But what was the job of Alan Turing, the character in that movie? Exactly. He's supposed to design a computer or help design a computer to decrypt messages that were encrypted by the Enigma machines. Okay, very good. So do you think there's a termination to that process of decrypting? Yeah, once it's decrypted, you're done, right? There's nothing else to do. So in Alan Turing's terminology, the program gets to a halt state, which means I'm done. Okay, there's nothing else to do. So this is where we borrow the word from. It's called the halt state in Alan Turing's terminology. Is that okay? So how many people think that this is the last class, the last time ever that you will hear the term halt or halt state or Alan Turing? Good. I'm glad that no one is saying that this is going to be the last time, because if anyone claims that in this class, that usually means that person is about to change major, which is not something I would hope on people. Yes.
How much does like the work of Alan? I mean, other than like you're saying specifically like Hall Slater talking about like breaking Enigma, how much does that feature in like upper division classes?
Aha, now that is a very good question. So the question is, I'm repeating it so that it's recorded. So the question is, how much of Alan Turing's work is part of the content of a computer science track, degree? Is that kind of a fair way to rephrase that question? Yeah. Okay. So what you do, okay, I'm not going to go through the whole process, but you can do it on your own. You can look into computation theory. That's one title of a class is computational theory. You can also see the Wikipedia page or on other universities what that means. Another name of the same class is called automata theory, and it basically refers to the same thing. So you're looking at state machines, okay? So some of you might have encountered the term finite state machine. Yes, no, kind of? Okay. FSM, which also stands for the flying spaghetti monster, but that's a whole different class. But finite state machine, okay, is a kind of automata, okay, which is the name that Alan Turing used to refer to computers, okay. So when you talk about automata theory, you're talking about Alan Turing's theory on computation. So the same thing with computational theory, okay, they're referring to about the same thing. So you look at an automata, okay, if you look into so there are three types of automata. One is called finite state machine, the next one is called a stack machine, and the last one is called a Turing machine. Okay, so I can easily look up Turing machine and go to images and find an example of a Turing machine. So in any type of these cases, okay, you have what we call states. So you have a halt state right here. So the halt state always has double circle to represent that this is the last state, nothing is coming out of the halt state. Do you see all the arrows? If you look at the other pictures, okay, just quickly, if you look at the other pictures, if they has a halt state, they don't get out of the halt state. The halt state is the last state. So the way Alan Turing models, computing is the computer at any moment of time is in a particular state. Now that state is complex with modern computers because with a modern computer you have the 16 registers inside the processor that you can program, plus I would say about maybe 30-ish other registers that you have no direct control over, and then you have all the content in RAM, right? Which is like 16 gigs. So all of that combined to a single state. Okay, the transitions here is one is this particular one is saying if the input is a 1, then we'll take this transition. If the current state is A and I'm seeing an input of 1, this is the transition I'm going to take. Whatever is on the other side of the 1, after the slash, is an operation or quote unquote output. So when it sees a 1 in state A, it would output P, L, and then it would transition to another state which is C. Then you're in C state. In the C state, if you see a 1, it would transition to the halt state, and at the same time it would output PR in this case. But if you see a 0 instead of a 1, then you would transition to state B and output PL. That is a state machine, okay? And the interesting part of Alan Turing's theory is this theory, as simple as it seems, right? It's really, really simple. But computationally speaking, it can model the most complex computer that we have today. So when you look into theorems of what is computable, what is not computable, the Turing theorem is one of the interesting one. The halting problem, okay, it's called a halting problem. The halting problem is basically saying, is there an entire class of problems where no machine can solve, in theory? Okay, and it describes, what type of problem that no machine can solve. So when you get into this class, computational theory or automata theory, you would think, hey, our modern computers are so much more complex than Alan Turing's machines. But the thing is, his theories still apply to the most complex machine that we have today. Yes?
Is this how Google was testing their quantum computer to see if it used or if it was if it had quantum supremacy?
Mm-hmm.
They use those set of instructions.
I'm not sure exactly what the term, quantum supremacy means, from Google's perspective. I just know that between Google and IBM, they have experimental quantum machines that are quote unquote operating. So if you look up what a qubit, a qubit is, qubit, it is a quantum bit, okay, which is not the same thing as a regular bit because it is not deterministic. And so you have to, and everything that is quantum is probabilistic. So you can see the state of the spin state of an electron, right? It is either up or down, okay? So let's just say that there are two states to something. But because of the probability kind of thing, you cannot just observe it once and say, oh, it's up. No, it's up only because for that particular observation. You have to observe it like many, many times to understand what state it is actually in. Because you might find that 66% of the time is up and 33.333% of the time is down. So the state of a quantum bit is not binary as we know it. And it is not also something that is deterministic where you can just look once, like using a voltmeter, you can look at the output of an electrical circuit and say, yep, it's definitely a high signal or low signal. You cannot do that to a quantum computer. So the whole concept of knowing what state it's in is already interesting, let alone how to process, how to transition or have input. Yep, but it's a good idea to keep track or keep an eye on quantum computing, even though we have no classes on quantum computing. And I doubt too many universities or four-year programs would have classes in quantum computing. So this is the kind of stuff that you have to do on your own on the side, okay, to understand. Well, if you don't understand the mechanism, which is quantum physics, it's okay. But you have to understand the impact of quantum computing and keep an eye on that, okay? Because right now, there are only, as far as I know, only IBM and Google has experimental quantum computers. And the government does not have one, okay, as far as we know. And you can probably see, this is a little bit on a tangent, but you can see how space exploration is no longer something that only governments can do, okay? And now computing is also, or super bleeding edge computing is also not something that only a government can do. The private sector is overtaking the capabilities of governments. And we are not talking about some third world country government. We are talking about a first world country who is, for the most part, okay, still in the top tier when it comes to technology. And even so, the private companies are already overtaking. And in the case of computer science, the private sector has taken over. It has already progressed faster than what the government can do. So it's interesting. You guys are entering into a very interesting era, where you will probably see private corporations being able to do things that even governments cannot do. Yep.
Is that why? Is that because the private sector pays better? So the better people who can actually do this, or is it just more so they just want to contract out?
I explained this in another class, so this is just my way of looking at it. So if you look at the revenue of the government, okay, how does the government get its revenue?
Taxes.
And loans, right? They can borrow money, okay? They can borrow money from you, they can borrow money from possibly another government, but the income of a government is limited, okay? Basically it's just taxation. What about the income of a multinational company, some company that can trade across the borders of countries like Amazon, like Alibaba. Okay, so what is the income stream of that entity?
Them selling a product or service.
It's profit, right? So it's profit driven. So which one has an inherent limit and which one does not have as much of an inherent limit as to how much income it can get?
The government has a limit.
The government has limitations, but private corporations, especially international corporations, do not have as much limit. Now, if you're talking about corporations within a certain country, it would be the same kind of limitation as a government, because you're talking about people who are within that country who can actually buy stuff and generate the revenue. But when you're talking about international companies, then you're looking at the entire globe. Okay, if one company or if the citizens of one country does not have the money to buy stuff, hey, guess what? There are hundreds of other countries who can still buy stuff. So I think that partially answers the question of why the private sector can now do things that even governments cannot do. The second thing has to do with do you think whenever a private company needs to make a decision, let's say Google or Facebook, okay, and say, do we want to invest money in quantum computing? Do you think that process is going to be lengthy, like what the government has to go through? Or do you think that process is relatively short, where the key people of the company just decides, yeah, I think that's a good idea. Do we have the money to do it? Yep, we got the money to do it. Do we have the people to do it? Yes, we got the people to do it. Let's do it, right? That's it. That's how the private companies work. They do not need to go through an election of any kind. They do not need to go through counting the ballots. Okay, how many of our employees thinks this is a good idea? They do not have to count or recount. if it's like 51 to 49 split, it go like, let's recount. No, they do not count at all. So I think those two combined is partially why the private sector can move at such a speed that governments cannot. Even a dictatorship, even when it's like one guy says, we're going to do this, we'll do it, they still cannot compete with the resources that the private sector has access to. Yep.
So speaking of resources, I would imagine that the internet greatly increased everyone's access to information, and then I feel like companies can then just get more knowledge and use it.
Yes, but it also gives more reason for the private sector to invest money in quantum computing. Okay, so if you look into the rationale of IBM, Google, and probably Facebook, why do they want to have supremacy when it comes to the amount of computation power and also the kind of computation they can do? Like, because quantum computers opens up new possibilities that we can only start to fathom at this point. So why do you think those private companies are pushing the envelope?
It's a niche market. No one's tapped into it.
Okay, but what would massive amount of processing power buy when you are Google or when you're Facebook or when you're IBM? Yep.
Better machine learning algorithms.
Machine learning algorithms, and every single encryption algorithm that we have today are based on prime numbers, okay, or the factoring of numbers into prime factors. And because of the way the processor we have today, they're all sequential. You might say, but I can get a 16 core or whatever, right? It's still sequential. Within the processor core itself, it is still sequential. So encryption algorithms, they're still effective. Quantum computing is going to change all that. Okay? Yep.
Does that mean they can, like, if people did that, or if they came out with a quantum computer
Yep.
that achieves quantum supremacy, does that mean that they could crack pretty much any, like, password code they wanted to?
So if you look up okay, to answer your question, if you look up quantum computing and cryptography, you will find lots and lots of articles that talk about how once we have quantum computing, none of the current cryptography method is going to work, because quantum computers can crack prime number problems that we have today at a much faster speed. Now, does it mean that we cannot crack encryption today? That is not a true statement, okay? We can crack encryption today. It's just the problem of by the time you crack an encryption, the value of the message that you are decrypting is already gone. So if you think about Alan Turing's days, okay, so this is back to the movie, okay. Do you guys remember, what they were doing, at the beginning of the movie?
They're trying to decipher it instead of crack the actual code.
But they have already been doing it, okay. So the thing is, they have been doing it manually already, and that's part of the exam. Do you remember, the woman, who was later on, part of the team of Alan Turing, she aced the test. Do you remember? And there were a few interesting conversations, in the process because I think she was the only girl in the test group, right? Okay, so they were already decrypting messages already, okay? The Germans introduced a fifth disk into the Enigma machine, which increases the number of possible combinations of the encryption key to the point that manually decrypting will no longer give you the result within the time frame when it is useful.
They change every 24 hours, right?
Exactly. And also, when you think about military missions, okay, if by the time you decipher the message, the event has already happened, then there's no value to decipher anymore. So it is not about the possibility of deciphering something, it is about the timeliness of deciphering something. And quantum computers will change that. So right now, if you look at the US government, okay, it probably has enough processing power to decipher, messages. Like if you send something using, if you use SSL, okay, and you communicate, and the government intercepts your end-to-end encrypted message transmission between you and the bank, I will bet you the government can crack that encryption in about an hour. Okay. But we are talking about a massive amount of traffic going back and forth, and why would the government choose you, right? Have you done something? Right? You have to do something truly extraordinary in order for the government to say, we're going to put all the massive processing power behind us to crack the communication between you and whatever entity. Okay? Because they don't have that capability to crack every single message or every single transmission. Is that okay? With quantum computing, they can. But the more interesting part is if Google or Facebook gets there first before the government, what is going to happen?
They could crack all your data and just sell it off after that.
Exactly. So they have their own rationale, right? Facebook, Google, IBM, they all have their own rationale of going after quantum computing. But I will probably be safely bet that they will get there before the government. Yep.
Wouldn't that be illegal?
Why would it be illegal? There's no law to make it illegal at that point.
Is there no law that says you can't crack encryption?
Think about it this way, okay? If there is no law, if there is a law, okay, to say that this is not legal, don't you think those corporations will change that?
Yeah.
Change the law. If you don't like the law, change it.
Probably.
And how would they change it? If you already have the capability of deciphering any communication effectively, okay, what can you do to change the law? Well, if you can already know what is going on between the Congress people, the senators, and whatnot, because you have been deciphering their communication for a while, don't you think that makes it kind of convenient for you to find out who might be on your side and how you can convince them to change the law so that you, as a private company, is now legal to decipher messages?
You just create a better argument since you already know theirs.
Hmm?
You can just create a better argument since you already know theirs.
Yep, exactly. Well, there may not even be a need for an argument. You are correct about that. Because if they know the encryption key, they can just put that into the law. Did we vote on this? Yes, we did. I don't remember. Well, go check the records. Oh yeah, yeah. Even though we are using blockchain with 512-bit encryption, yep, we do have that event recorded. This law was passed, and this is how you voted. Really? I don't remember a single thing.
Is there any unscrupulous reason that someone would want a quantum computer? I mean, is there any?
Well, governments want it too, right?
Besides
Governments want it
government.
for many reasons.
Well, I mean, I understand the applications for government, but other than breaking encryption unscrupulously, is there any reason? Like,
I think it's going to change the whole AI field and machine learning as well. If you guys think about, I know this is really off topic, but if you think about AI today, okay, neural nets, okay, the computer science club just did is it done or is it still going?
No, there's still another part to it.
Another part to it. Okay, so the computer science club is still working on a workshop on machine learning and artificial intelligence. So you might think, oh, we are already there. Okay, we got it already. But if you talk to people, practitioners in neural network computing, you will know that in order to change the configuration of a neural net and see if the current configuration in terms of the number of hidden layers and also how things are interconnected and whatnot, in order to find the optimal or the correct configuration is expensive. Because let's just say that you're trying to find a correct neural network solution to a particular problem. But you don't know how many hidden layers you need. You don't know how the neurons are supposed to interconnect to each other. Is there inherent architecture to the interconnection? You have to experiment, okay? And to run those experiments is very computational intensive. So even with the resources that Google, Amazon, and all of the other companies have, you will still be racking up at least thousands upon thousands of dollars of using the cloud service to run your experiments. So we're not quite there yet, okay? Because we are still compute bound, okay? How much processing can we do? Even if you pay a lot of money, you can only buy so much. With quantum computing, that will change. So that means certain algorithms that are not practical to use today will then become practical to use. So that is going to change the landscape of AI as well. And if you change the landscape of AI, particularly machine learning, that is by itself a disruptive technology that feeds back into the whole loop. So machine learning and AI can potentially lead to the advancement of quantum computing itself. It just forms a loop where technology will just kind of feed back to itself and increase the pace to a point where we do not recognize, we cannot even anticipate. Yep.
So would that essentially make Bitcoin mining obsolete since the
Oh, absolutely, yes. Bitcoin, the current way of mining Bitcoins will just become totally useless. People will be finding coins everywhere. So whatever coin you have at this point will basically worth nothing. Yep, exactly.
all cryptocurrency would be crashed?
Oh, there won't be any cryptocurrency anymore, or at least not in the way that we know it now. Yep. So people will have to find new ways to do encryption in the presence of quantum computing. So all of that stuff is super exciting, and I think many of you will see that future. Okay, I know right now people look at the quantum computers and go like, that's a toy. Okay, that's a multi-million or maybe hundreds of $1 toy. But I think you will see it. You will see the day when it becomes reality. And by that time, hopefully you remember and go like, yeah, Tech said something about this 40 years ago. Because it's all on YouTube, it's being recorded. And YouTube, it will still be around. So we are running out of time, okay? There's a new lab today on 3 new instructions. We didn't quite get to the new instructions, but I did lead you through the analysis of the instruction that we talked about today and also on Wednesday. So that is going to help you to do this particular lab, okay? So I'll see you guys over at the lab in about 10 minutes.